So the topic for this afternoon is integrating clickstream data in Solr for ranking and dynamic facet optimization. And I'm Ilayaraja from Target. I fly to here from Bangalore. I'm working out of Bangalore for search team. And so how many of you know Target? All right. And how many of you have used target.com? Oh, that's quite a bit. Do you like the search on target.com? Okay, I don't see any hands. Okay, all right. So, yeah. So this is the agenda for the talk. So mainly of how we can use the clickstream data for enhancing the search ranking and relevance. And the second application that I'm going to talk about is for bringing in right filters for a search query. So I hope that people here have an idea about or the concept of clickstream, right? So of course, like you can apply clickstream for different applications. You can build type ahead, spell checking, related searches, recommendations, and classification algorithms using clickstream data. So we have done all of these things, but I'm going to focus on couple of main applications, ranking and facets, and we will try to deep dive as much as possible during this talk into how we have leveraged the clickstream data for implementing these two algorithms. Right. So moving on. So the first application that I'm going to talk about is ranking. This is the architecture that we are using for clicking the, getting the clickstream signals, and how we are, crunching the data in a Hadoop-based cluster using Spark, and what kind of data is coming as output that is used as the relevance or ranking signals. How do we feed that back into the Solr engine? And how is it used at the time of search? So this is what I'm going to walk through in the slides that is coming up. So the signals that we catch here are given a search term, what are the different items that the guest is engaging with, the clicks on the items that we show on the search results page, and what items they have added to the cart or what items they have eventually purchased in the funnel. So these are the signals that are mainly used in building the ranking solution. So we take these signals and we maintain a database something like this, which has the user ID and the session ID, timestamp of the event that occurred, and the particular action type, whether it's a search action or a product click action or a cart add action, and the corresponding meta information about that action. In this case, it's the search query. The second case is the item ID, which is a unique product ID, and the position of that item as appeared on the search results page, which is very important as we see further and see why that position is important. So we get this kind of data information from each of the web server logs, which is running our search service. And we feed back those data into a Hadoop cluster to do our MapReduce jobs using Spark. We aggregate these informations over different sessions and actions. And in the ranking application, what we were interested to get out of this MapReduce jobs is, given a particular item, what are the list of top queries for that particular item, according to a scoring algorithm that we are going to see, right? So when we get that mapping of item to the top queries, it is feedback into the Solr during the indexing of the documents. So each document in Solr is an item, so we add extra fields to those items. So every document has a title, brand. Apart from that, it will have a list of top search terms associated with that particular item, and the corresponding click values that refers to the ranking score that we have computed using our algorithm. So that's what we index for every item. And then during search time, the same data is used, and the Solr function and boost queries are applied on this data to get the re-ranked result set. And that is feedback to the user again. So this is like a implicit feedback mechanism and the flow that we are using for ranking. So going forward, so as I'm talking about Clickstream Signals, so obviously you need to look at like different factors here. So the two main factors that we are considering is product clicks and products added to the cart for a given search query. And then we take a weighted average of weighted summation of these two signals, giving more weight to the cart add rate. This is right now is like a manual configuration, but we are trying to learn this in a better way. I will come to those in the further slides. So we use the position information to address the positional bias of the search results, because users are always tend to click on the top results despite whether it is relevant or it's not, it may not be that relevant. Even then they click on the top results because it is shown on the top of the results page. So we discount for that factor, and so this is the kind of curve we use. So the x-axis is the position of that item in the search results page, and the y-axis is the weight. So you can see like if the position is on the top, let's say the top 2 results page, like 48 results on the search page, it is discounted because it is less than 1. After that, it remains 1. So when you multiply this weight to the formula I have shown here, sorry, on the click rate and the cart rate, so it is going to discount for that positions, and you will give more weights to items that have clicked, which is down in the results page. So it's like a relative positioning feedback of the clicks. And the second is obviously like you apply some time decay for the clicks. So recent clicks have to be considered very relevant. So here the x-axis is the number of days from which the click had happened. So as the days increases, the weight is going to decrease as well. So using these notions of time decay, position weight, and also we consider newness, so all these factors put into the scoring formula, what we compile is output data which is of like this, where for every item we get the top search queries, list of top search queries, along with the corresponding click rank score. So this file is feedback for indexing into Solr, and this is the integration logic that we are using. So we create 2 dynamic fields. One is the click term, and other is the click values. So this will help us in putting as many click terms as you want. So you keep that as a dynamic field. So you can add 10 top click terms for the query, or 20 or 30 as you want, and corresponding click values, which is the rank score that you have computed for each of those click terms. And then at the search time, what happens is, as I said, we use the boost queries. So in this case, for the query Nespresso, we look for the exact match of the search terms with each of the click terms that we have indexed, and do a multiplication here with unquery, that only if this match is true, we will be going to add this boost query, BQ, to the original search query that we are firing. So the original search query will also have other things like title match, category match, brand match, etc. Along with that, it is going to look for matches in the click terms that we have indexed, which is coming from the implicit feedback data from the click stream. And use these weights that we have computed for multiplication and add it to the original relevance scores that we are computing from the TF-IDF vector space model. So that's what this is going to do. Yeah, so doing that, we have seen our results have been significantly changed. So for example, before putting this re-ranking logic, we have seen for query almonds, it was throwing some almonds milk and in the top results. And then after the re-ranking, using the clickstream signals, we have seen the almond nuts coming on the top. And also like Xbox, so we have seen some other results coming, and then we got the real games coming up on the top for Xbox. Yeah, so these are the metrics and measurements that we have done for this particular ranking algorithm. For offline, we have a human judgment team that judges like top 20 results for every search query. So what we do is we give like, we take top 20K queries of our search log based on the search frequency. And for every search results, we compile like top 20 results that are shown before and after the re-ranking and give it to our judges for doing the relevance judgment. So once the judgment data is available, we use the NDCG score for getting the relevance score for the search engine system. And the other metrics that we use are click and cart rank. These are like a sanity measurements because what click rank works like this. It looks at, for a given query, what are the items which are having more clicks in the logs. So it will take that and have a intersection with the results that we are showing now. So it will see like what is the intersection that is coming up. And similarly, the cart rank. And the other online mechanism for measuring relevance is that we run the A/B test, of course. And the primary metrics that we look for here is the click-through rate of the search engine and the conversions, and the search conversion. And the secondary metrics is the demand sales, because demand is not something we can attribute directly to the relevance and ranking algorithms. It could also be affected by external factors like deals and promotions and the price, etc. So we take that as the secondary metrics for the success of the ranking algorithm. And this is the impact that we have seen using this re-ranking logic. So we measured like what is the improvement in the top 5 CTR, which means like in the top 5 positions of search results, what is the CTR click-through rate improvement that we have got. So it was about 10%, and yeah. So top 5 it was 10%, and yeah, I think that's top 5 is 10% and top 10 is 6%. Sorry for that. And the recall for the search is like 350K queries. As I said, we are doing the exact match for the search in the click terms. So it is always restricted by the queries that occurred in the past. So we may not be able to apply this algorithm for a new query. So that's one of the challenges that we are currently working on. But we could do the re-ranking for almost all the top queries of the system. So it improves the top line. It gives better click-through rate, while it doesn't improve that much of the search conversion, because helping the top queries need not necessarily help your top line. So that's the other challenge that we are facing right now. And of course, it has a 2% improvement in the demand sales when we have an attribution funnel towards the search conversion. Yeah, so as I said, like we are facing the challenges like how do we improve the recall of this ranking algorithm from 350K queries to million queries, right, on the system. you get more than million unique queries in the system. And the second challenge is like improving relevance and ranking for the top queries is going to give you better CTR, but not necessarily a better search conversion and better demand. So as long as you don't worry about the long tail queries, you cannot improve the search metrics and the search conversion rates. So to scale up this algorithm, we are trying to use the learning to rank plugin, which is developed by Bloomreach. So right now, it's in a prototype stage where we have identified like list of features that we want to train the data upon. So the training data that we use is the same clickstream data in this case, because it can also use a human judged data, but getting human judged data is very costly. So we are using the clickstream data as the training data in this case. And so we use these features to train the model. Basically, I've tried a linear SVM rank model in this case and identify the weights for the different features here. So yeah, so this is still a work in progress. So I will move on to the next application for this talk, which is the facet optimization. So facets are very important for search experience from the guest perspective, because if your facet engagement is good on the site, it helps the guest to narrow down the search results as quick as possible. So they can find the relevant results that they are interested in by filtering the brand or the size and different filters that you show on the results page. But how do you know that what are the filters important for a search query? So doing this at a query level is a big challenge. Right now in our system, we have custom rules for different categories at a leaf level. So we have about 3,000 leaf level categories in the system. And for each of the leaf level categories, we have list of facets configured that is plugged in at the time of search and shown to the user as the filters on the search results page. So, but that's not giving the best experience. So our facet engagement rate is about 7%. So the challenge here is that how do we get a better facet engagement if we can leverage the clickstream data? So couple of applications that I'm going to talk about here is how do we reorder the existing facets that are shown, which is facet ranking. And the second is how can we discover more facets for a search term. So this is the algorithm that we are using for facet ranking. So it's going to compute us 3 different relevant signals. The top relevant signal is the facet engagement rate, which is equal to the number of facet clicks and normalized with the facet impression. So for each of the facet types, like as I said, size or brand, etc., what is the total total clicks that this facet type had received with respect to a particular search query, and then the facet impression is equal to search impression in this case, because every time you search for that particular query, you always see the facet that is configured. So that's facet engagement rate. And the second relevant signal is the product click association. So looking at the funnel of filtering, so after clicking a particular facet type, did the user go ahead and clicked on any items after the refinement? So which is very important signal, because that tells you that this particular facet type is very important for the search query. So that's the second signal. And again, it is also normalized with the search impression rate. And the third is the add to cart signal, which is, again, looking at the funnel of filtering and refinement. So all these 3 factors are summed up with a weighted multiplication. Obviously, the weights for the caught and clicks rates are better or more compared to the facet engagement rate. So what we get out of this is for every search query and a facet type pair. So if the query is blue shirt, for blue shirt, facet type brand as a score, and for blue shirt, facet type size as a score, and so on, color, for example. So we get this listed order of search query to facet type scoring, and then we use that to reorder the facets at the time of search. Yeah, so this helps in reordering the existing facets. It doesn't help us discovering the right facets for the query. So that's the other challenge I'm going to talk about. So basically, in this case, what we have is a custom rule defined for every leaf category or a breadcrumb level. So it is easy to do that manually because the number of breadcrumbs that you have in the catalog is very limited. So you can have a refined list of facets for every leaf level category or a breadcrumb. So that is what we show on the browse results page. So the browse results page can contain more facets, while search results page may not show that many facets. The challenge here is how do we map those search queries to a particular category so that you can leverage the rule that you have to show those facets belonging to the breadcrumb back on the search results page. So this is more like a classification problem. So what we have done is built up a query to category mapping algorithm, in this case using the click signals and the caught at signals, and use that to map a query to the category or a leaf category so that we can show whatever facets we are showing in the breadcrumb back on the search results page. So for blue shirts, if we were showing only a default set of, let's say, the size, color, and brand, but if you look at a particular category page, let's say T-shirts, it can have other facets configured like T-shirts, neck type, and so on. So we can map those facets back to the search query and show as part of the search results. So this is the architecture that we are using. So this is different from the ranking model that I talked about. In case of the ranking of search results, the relevant signals are indexed back into the Solr engine using the click term and click values, if you remember. Whereas in this case, we are not putting that back into the Solr, but it is used as a microservice, which is hosted as a separate service that gives, for a given search query, what are the list of facets to be shown based on the model that is compiled. So this is our search service layer. So the search service layer gets the facet mapping from the facet ranking service and also gets the custom rules mapping from here and aggregates those two list of facets finally to show the results to the user query. And this is the HDFS that gets the clickstream data and compiles the facet ordering and discovery model and copies that as a file back to the service so that it is available at the time of search. Yeah. No problem. Yeah, so this is the impact that we have seen after discovering and reordering of search results. So for example, threshold drug Solana, this query got only about 7 facets before the model was applied, but after the model was applied, it could be able to discover the right facets In this case, you have got like primary pattern, decor style, primary material, etc. And also you can see the order in which the facets have changed. So color was not the second top in this case. It is now on the second and so on. And the overall impact of the algorithm is like number of newly discovered filters on the x-axis, and the y-axis is number of unique guessed queries. So what it says is like about 70K queries in our search have got at least 6 more filters discovered from this model, apart from just reordering them. Right? Yeah. So that's all I have. I give more time for the Q&A if anybody have any questions. Yeah.
How do you deal with click bias? Do you find that you have people click on bad results, describes even worse
Yeah. Yeah. So we have seen that definitely, and so when you use a clickstream model on which is like taking absolute relevance as an absolute relevant signal, it is always going to be a problem. And to avoid this, we can use randomization in the computation logic. There is a paper, unbiased learning from clickstream signals. So I'm trying to experiment that. It's by Professor Joe Chims from Cornell University. So there are a couple of techniques applied in that. One is randomization of the results, so that you don't show the same results to the user. So you randomize it in the top results page, so you can eliminate that bias of presentation. Anything else? Yeah. Hmm? Hmm? Yes, correct. So we are using these two signals. Sorry, the question is that what are we trying to compile, right? So are we trying to compile like top click terms for a given query using these two signals is the query, right? So yes, so actually it is done like a reverse way if you look at the data, because for every query that the user fires is clicking on set of items. So what we compute during the MapReduce job is that for a given query, what are the top n items and the corresponding score. And then we reverse this mapping, because in Solr, every document is an item. It's not a query. So we reverse this mapping. So we get like for every item, what are the top n queries, so we can put it in the index. So that's what we compute. Hmm? Okay, so, so the question is, how is it applied at search time? So as I said, it is applied like a exact match. We are not doing a re-ranking here, like we don't fire the original query and get the results and do re-ranking. So that's not happening. So what is happening is that, say if the query is blue shirt, so the Solr query goes like title match with blue shirt, brand match with blue shirt, etc. Those are the relevance fields that you have configured. Along with that, it is also going to look for blue shirt in the top n click terms, which is indexed against every item. So let's say an item X is part of the result set for blue shirt based on the other fields like title, brand, etc. So it is going to look at whether this item also contains the click term equal to blue shirt. If it is click term 1, which means the topmost click term is blue shirt for that item, so it is going to use the boost value that you have also indexed for the corresponding click term as click underscore value as the BQ query. So it is going to add that value back to your TF-IDF score. Is that clear? Yeah. So,
You talked earlier about expert rankings with relevancy, or I don't know if you call them expert rankings, but human judgments. I didn't quite get, if you could just review like how many you did and how many judgments they made on how many searches total. Can you
Yeah.
just go over that?
Yeah. So the question is about what is the human judgment data that we have got for evaluating the results. So what we have done is we got top 20K queries based on the search frequency. And for every query, we got top 10 results before and after the algorithm. And we gave it to our judgment panel to judge, give the relevance scores. So basically, they give you a relevance score like 0, 1, 2, 3. 0 means totally irrelevant, 1 is better, 2 is good, 3 is best relevant match. So we get 0, 1, 2, 3 for every query to item, and then we use the NDCG algorithm or the formula for finding the relevance of the search system.
Do you just get one judgment per document or per query? Or do you get multiple judgments from multiple people?
No,
Okay, just one.
just one.
Okay.
Yeah.
Another question, right? So take an example, going back to the query, use the fixed data, right?
Yeah.
For getting the products off of the list, right? Suppose if there's a launch on Xbox One, right? And it's called Xbox One Credit,
Mm-hmm.
right? And you have a lot of clicks on that, right?
Mm-hmm.
And after 6 months, Xbox launches Xbox One Fourth Edition,
Yeah.
right? So this is a new product which is launched, right? And it doesn't get any click, right? Now
Yeah.
somebody looks for Xbox One, right? So which one will come on top? Because Xbox One, older one, have a lot of clicks in it, right?
Yeah. Yeah. So there is one more parameter that we are using, which I haven't put up, is the newness. So that is taken as the function of the launch date of that item. So that goes again into this formula of re-ranking. So the newness is taken care of, but it's always a challenge, like whether you give more importance to newness or you are going to give importance to the click rate. So if you put up like manually configured weights for these different signals, it's not going to work for the entire search because it is very specific to specific to a category or a search query. So that's why we are trying to use a learning to rank model. So we can, if you look at the features that I have listed in the learning to rank slide, it is also having a feature called recency. So how much weight should be given for recency can be learned using the machine learning model in this case. Sorry.
So for the facets, right? So have you tried using visual navigation? Because we have seen with the customers, right, that it has more engagement, with the customers when they use visual navigation. It's like 70% more.
No, we haven't done that. Yeah.
So do you also give importance to things like brand reputation and you're a retailer yourself, but
Mhm.
usually there's like a lot of retailers where we give like retailer importance or merchant reputation into account when choosing the products.
So we haven't done this for this re-ranking logic, but what we have developed is another popularity scoring algorithm, which is independent of the search queries. So popularity ranking or popularity score is computed for every item that is there in your catalog. It is more like a page rank of the Google search, right? So every website or a web page, what is the importance of that web page based on its anchor links and things. So if you consider similar algorithm, what we have developed is a popularity score algorithm, which will give weight to the document or an item based on which brand it is, based on how many times this item was clicked overall, irrespective of search queries, and so on. So this helps us in breaking ties in relevance. We use this as a tiebreaker in Solr. We don't use this as an additive boost of re-ranking because of the limitation that it is not with respect to a particular search query. So there we use the brand as the signal for scoring. Yeah. Yeah.
So you talked about identifying new facets.
Hmm.
I think that's what is the
Category. Yeah.
So how do you handle that for longer term? When you can't identify what the category is, or you come up with a category?
Yeah, That's a great question. So if you look at models like naive-Bayes classification, we don't necessarily have to match the long tail query, like an exact match to classify to a particular category. What we will do is tokenize the query into multiple tokens and compute the conditional probability with respect to the category. So that way it can help us to improve the recall. It may be a challenge with respect to precision, but what we have observed by using a naive-Bayes classification is it gives us about 90% recall and about 85% precision. So that way we can able to cover the long tail classification as well. Sorry, can we take a query from that side? Sorry?
The scores, like how you
Yeah.
decide from the Clickstream, this is a 3, this is a 2, this is a 1. Like, what are your thoughts on how you're writing the Clickstream into those labels, like the human judgments you had mentioned at the labels?
Yeah, right. So the question is like, how are we using the clickstream signal as a training data for learning to rank, right? So, so in the absence of human judgment, we are trying to use these signals as the training data. Obviously, this is not as better as the human judged data. And also, the clickstream signals is definitely is going to give us a biased data. But it is still a valid implicit feedback of the relevant signal. So that's the basic assumption. So what we get is for a given query and item, what is the score based on the clickstream signals, and use that in the training part. So of course it's challengeable, but we can also look at randomization and other mechanisms, as I said before, to avoid the bias of the clickstream signal. So the question, there is again like another paper which talks about how can we simulate human judged data from the clickstream signals, which is in a closer way, eliminating the bias and things. So I'm looking into that as well. You can check like, just search for Joachim's, Joachims. Yeah, SVM Light author, Joachims, from Cornell University. Yeah, you can search like simulating human judgment data from clickstream signal, something like that. I can give you the title later. Yeah. All right, so any more questions? So we have time? One more? So, sorry.
Does your algorithm takes care of the zero?
Null queries, you mean, right? No, so this doesn't worry about zero results. We are only re-ranking the existing results for the query. We have other mechanisms for addressing the null queries where we use techniques like tome dropping. Yeah, right. Just take one more question, the last one.
I was just curious on the query term matching. You said it was all exact match.
Yeah.
Like blue shirt. Like so you're not doing any stemming, so blue shirts, and then or synonyms like the shirt.
We are doing normalization of the query. That means we are applying stemming and spell checking, but we are not applying synonyms. That's the limitation. So we get a recall of 350K in this. Yeah. Right. Okay, thanks.